Now let's look at another experiment. This time, instead of just rolling one die, we're going to roll two dice, and then we're going to add the two faces together. So the experiment is to roll two dice and record the sum of the faces. First of all, we have to figure out what the different outcomes for this experiment would look like. So I set up a little table, got the first die and the second die. We're going to take those and add them together. I'm going to fill this table in with all of those results. Now we want to look at what different outcomes we have in this table so that we can do a probability distribution for those. If we look at the different values that we ended up with, we have a 2, a 3, a 4, a 5, a 6, a 7, and all the way up to 12. Now for our probability distribution, we want the probabilities for each one of those. And for that, we have to go back and look at what was happening here. We had the one die being rolled and the second die being rolled. Each outcome on each die was equally likely. What we ended up with was these 36 entries in this table up here, since we have 6 rows and 6 columns, and each one of these entries would have been equally likely. We can figure that each one of these entries, the probability of it would be 1 over 36. And that's what we can use to get the probabilities for our different outcomes. All we're going to do is take the outcome, see how many times it comes up in the table, and then we're going to have that number over 36 for our probability. So for the 2, that only comes up once, because the only way that can happen is if both dice are a 1. So the probability for this is just going to be 1 over 36. Then for the 3, that happened twice in the table, so that probability is 2 over 36. For the 4, there are 3 4s in our table. For the 5, there are 4 of those. For the 6, there are 5. And for the 7, there are 6. Now looking at this pattern, you might think that this is just going to keep going up, but actually what happens is when we get above 7, it starts coming back down, because if we look at the 8s, there are only 5 8s. So that probability would be 5 over 36. For 9, it's 4 over 36. What ends up happening is this goes back down to where when we get to 12, it's back down to 1 over 36. Now I'm going to go back for each one of these and put in a decimal approximation. This gives me my probability distribution because I have all of my outcomes as numbers and I have the probabilities for each one. I could check my probabilities by adding them all up. If I do that, I'm going to get 1 if I add it up with the fractions, and if I add up the decimals, it might be just a little bit off because of rounding error. But it's going to be close enough to 1 just for me to be able to check and make sure that those are right. Now what we can do once we have this probability distribution is we can look at a graph. And I did a bar graph instead of the histogram because this is actually a little bit more accurate when we've got discrete values for our outcomes. And from this bar graph, you can see pretty easily how symmetric this distribution is. It looks kind of bell-shaped because it does start out low on each end and then it has a high point in the middle. It's definitely symmetric. The other thing that we could tell pretty easily from looking at this graph is where the center of our data is, and that would be at 7. That's the highest bar, and it's exactly in the middle of all these. Now we're going to look at a different experiment. In this one, we're going to play a game. We're going to use a spinner that's half blue, 1/3 red, and 1/6 yellow. Let's look at how we would write our probability distribution. I've got this filled in already with just the colors and the probabilities for each one. But if we want to make this a valid probability distribution, we need to fill in some kind of numerical values for the outcomes. What we're going to do if we want to treat this as a game is that we're going to say that depending on which one of these outcomes you get, that you're going to win a certain amount of money. Let's say that for the blue you would win $1, and that for the red that you'd win $4, and for the yellow that you would win $7. Now we've got some numerical values that we can put in for our X. Now how we put these in depends on whose point of view we're looking at this from. Right now we're going to look at this from the player's point of view. So if I'm playing this game, I'm going to put these outcomes as that I'm winning money each time. That means my outcomes here are going to be positive numbers. So I have a +1, +4, and +7. To make sure that this is a valid probability distribution, I would want to make sure that my 3 probabilities do add up to 1. And if you go through and add the fractions, yes, they do add up to 1. There's no condition on the values of x except that they have to be numbers. They can be negative or positive. They don't have to add up to anything in particular. For this one, if we want to find the expected value of the game, that means we'd find the expected value or the mean of the probability distribution. So this is where we're going to do the x times the p of x. Just going to take 1 times 1/2 here. Here, this is going to be 4 times 1/3. And this one's going to be 7 times 1/6. So to get our mean, or our expected value, we're going to take those 3 results and add them together. That's going to give us 18/6, which is 3. From the player's point of view, the expected value is $3. What that tells us is that if we were going to go and play this game a whole bunch of times in a row, this is the average amount of money we would expect to win per play. The answer to this is that we would expect to win an average of $3 per play, played this game many, many times. The expected value is always about what's going to happen in the long run. In the long run, if we played this game 100 times or 1,000 times, and then we went back and added up all our results, that the average amount we'd win per play would be $3. Now that doesn't mean that we're winning $3 on any one play. We can't, because that wasn't how our game was set up. We're either going to win $1 or $4 or $7. We're never actually going to win $3. That's just the average per play. Now once we know that, we could figure out how much money we could expect to win if we played this game 30 times. So in 30 plays, if we're averaging $3 per play, 30 times 3 would be $90. And for 100 plays, then we'd just be taking 100 times our average per play, which would be $300. Now let's do one more variation of this. If we make this into an actual gambling game where we could lose money, one way to do that is to make the player pay $4 before each play. Let's look at how that would change our outcomes and our expected value. So this time, if I'm playing, I've already paid in $4 before I play. If I get a blue, then I win $1. I put in 4, I got back 1. I've actually lost $3. To signify that I lost the money, I'm going to put this in as a -3. This time this is going to be my gain or loss on the play. A loss I'm going to put in as a negative number. If I get a red, then I put in my $4 and I would get back $4. So that means I broke even. My gain or loss is 0. If I get a yellow, I put in $4, I got back 7. That means I won $3. My net gain was $3. Now if I want to figure out my expected value, I'm going to take each of these and multiply them together. Now I have to be careful here, because if I have a negative value over here, I have to make sure and include that when I do this. So this is going to be -3 times 1/2. This one is 0 times 1/3, which is going to give me a 0. This one is a +3 times 1/6. That's going to give me a +1/2. If I add these 3 together, that's going to give me an answer of -1. This means that my expected value is a -$1. I can expect to lose an average of $1 for each play. This time, if I played this game 30 times in a row, I'd expect to lose about $30. If I played it 100 times in a row, I'd expect to lose about $100. If we look at this from the operator's point of view, that just means that our gains and losses are going to be switched around. The expected value from the operator's point of view is a +$1, which means that the operator can expect to make an average of $1 per play. This is exactly how casinos and gambling games make their money. They might not be making a lot per play, but they're dealing with thousands and thousands of repeats of a game that's being played. Even if their expected value is only a little bit of gain per play, still in the long run, they're going to end up making a lot of money.